On India's eastern coast, the port city of Visakhapatnam is transitioning into ground zero for a gigawatt-scale industrial experiment. Google and the Adani Group are committing $15 billion to the region over 5 years. Their goal is a 1 gigawatt artificial intelligence data center, linked to global networks via high-capacity subsea fiber optic gateways. State leaders are highlighting the economic upside. Chief Minister N. Chandrababu Naidu claims this facility will support 188,000 jobs, framing it as a primary engine for a developed India. Processing artificial intelligence at this scale requires a heavy physical utility. The digital cloud depends on sprawling warehouses packed with hardware that operates at the edge of its thermal limits. While the public relations campaign presents a vision of high-tech prosperity, the engineering reality suggests a hidden terrestrial burden that complicates the official narrative. Once the temporary construction crews depart, the completed AI data center functions as a ghost town. These are highly automated, sterile warehouses governed by software, requiring very little human presence. The few permanent roles that exist are highly specialized. Typically, these network engineering and cybersecurity positions are filled by external recruits, leaving little room for the local workforce. The center's primary function is to support the hardware. Training a large language model requires a different architecture than traditional cloud storage. AI relies on dense clusters of GPUs, which run at peak capacity for months at a time. This chart shows the electricity gap between the two. A standard IT server rack draws about 7 to 10 kilowatts. An AI-specific rack can demand over 100 kilowatts. Operating thousands of these racks creates a 1 gigawatt load. This requires a dedicated high-voltage transmission network and places a relentless baseload pressure on the regional power grid. These facilities prioritize the conversion of raw electricity into computational power. They are machines engineered for density, not engines designed for human employment. Concentrating that much electrical current produces extraordinary heat. To prevent GPUs from failing, operators must pump continuous streams of liquid coolant directly through the hardware. This block represents 2 million liters, the daily water intake for a standard 100 megawatt data center. Multiply that for a 1 gigawatt campus, and the daily industrial thirst reaches 20 million liters. Visakhapatnam is already a region of high water stress. Local residents face erratic rainfall and depleting groundwater. Using millions of liters of fresh water for industrial cooling creates a direct conflict with the community's drinking and agricultural needs. To secure this resource-heavy facility, the state government offered a 22,002 crore rupee incentive package. This includes tax exemptions, land allocation, and discounted utility rates for the next 20 years. The local public is effectively subsidizing a $1 trillion conglomerate to utilize their most limited natural and financial resources. The Visakhapatnam project represents a trade-off. The community provides its land, grid capacity, fresh water, and tax base in exchange for a closed, automated fortress. Tech giants gain the raw compute power needed to win the AI arms race. The local population, however, must manage the resulting utility scarcity and the long-term environmental burden. While the technology sector is often associated with software and office jobs, hosting AI infrastructure is a model of heavy industrial extraction. It is a process of turning local resources into global digital intelligence. This pattern is accelerating worldwide. As more regions compete to become tech hubs, local governments must look past the glossy PR and calculate the true costs of supporting hyperscale data centers. The cloud has a heavy physical footprint. If leaders fail to account for the terrestrial toll, these megacenters will compute a permanent loss for the local taxpayer.